This slide series is called Investigating Intermolecular Forces, and it involves an AP chemistry lab that will be done at some point in the future. We're going to ask the question, are there differences in the physical properties of compounds that have the same empirical formula, the same molecular formula, and therefore the same molar mass, but have different structures? We're going to talk about intermolecular forces and structure. A future lab investigation will ask the question, are there differences in the physical properties of compounds that have the same molecular and empirical formulas, and therefore the same molar mass, but different structures? Let's recall the types of formulas that we will run into. From the percent composition of a compound in the atomic mass of the elements that make it up, we get the empirical formula. That's the simplest formula. It's a ratio of small whole numbers. For example, for all of the carbohydrates, the formula is CH2O. Now, there is no such thing as CH2O as a carbohydrate, but that's the simplest formula of, for instance, glucose. From the empirical formula and the molar mass, we can decide what the molecular formula is. The molecular formula tells us how many atoms of each kind are in each molecule. It's a multiple of the empirical formula. What we do is we divide the molar mass by the mass of the empirical formula. That tells us how many empirical formulas are in the molecule. That's the multiplier that we will use, for instance, to get C6H12O6 for glucose, or in this case for ribose, C5H10O5. Finally, there is the structural formula. Well, that's not the last kind. We know that the same molecular formula can be put together in more than one way, especially true with organic, that is, carbon compounds, like glucose. So, for example, C2H4Cl2 is a molecular formula. It can be put together in more than one way. You might want to stop this and try to draw some pictures or put molecular models together to make this dichloroethane. Well, there's one. We call that 1,1-dichloroethane because both chlorines are on the first carbon. And this is 1,2-dichloroethane, where the two chlorines are on different carbons. Let's look at the structures and names of hydrocarbons from methane through heptane. By inspection, can you predict which of these alkanes have only one structural isomer? That is, you can't put them together in more than one way. So you might want to talk about that with a partner or try to draw some pictures and see what the answer is. Turn this off and then come back. Well, there are the three that have no structural isomers. When we get to butane, we can see structural isomers. Butane and what we used to call isobutane that's the lightest alkane that has two and only two isomers. And it's drawn, for instance, in the two-dimensional skeleton like this, and this is more of a three-dimensional way to look at it using molecular models. In this case, we've got a methyl group hanging on the central carbon. Here we've got what we call a straight chain hydrocarbon. Now this is normal pentane, the straight chain pentane. Can you draw other pentanes that are truly different, not just this thing twisted around? Well, here are the three isomers of pentane, C5H12, and you can see that in so-called isopentane, the end methyl group has been moved over to the second carbon, and in neopentane, the carbons on both ends have now hung off of that central carbon atom to make neopentane. They have different IUPAC names, of course. Now, here's an extension. You might want to try this and talk it over with one of your groups, because butane had 2 isomers, pentane has 3. A student deduces that a number of alkane isomers for a given alkane is 1 more than the number of carbons, and that begins with butane. Is that true or is it false? Now, the investigation you will at some point do is you're going to find the boiling point at 1 atmosphere of normal pentane, isopentane, which is also called 1-methylbutane, and neopentane. Another one occasionally we do is propanol and isopropyl alcohol. That is another thing to do. Now, if you look at these 36, 27.5, and 9.5, you see there is a definite difference in the boiling point at 1 atmosphere. So discuss, make a hypothesis. If the molecular masses, as they are here, are equal, what is causing these boiling points to differ? N-pentane, isopentane, neopentane. You'll notice as you go from here to there, the boiling points go down rather well. The future investigation will study normal propanol and isopropanol. First one's called 1-propanol, the other's called 2-propanol. This is 1-propanol. The alcohol, the OH, the hydroxyl group, is on the terminal carbon on one end, whereas 2-propanol, the OH, the hydroxyl group, is sticking onto the second carbon. And the investigation will ask if the boiling points of these are different. You'll heat both compounds, you'll track the temperature versus time curve, and you will look for the boiling point. It'll be obvious. But is there something else you could measure? Maybe if you put these molecular models together, perhaps you could look and see if there's a structural difference that might be what we account for the different boiling points using. Here are the alcohols again, and in a chromatography apparatus. And remember, chromatography works by the movement of the alcohols across some sort of fixed screening apparatus like paper, perhaps a paper towel. We've separated solutions or suspensions in that way, but say in a gas or liquid chromatography apparatus, should these two alcohols show peaks of separation. And remember, you want to measure something else about these structural models and see if you can make a correlation between that something else and either the boiling point or the chromatography separation.